Signal conditioning and the integrating amplifier. If you take an inverting amplifier and you replace the resistor in the feedback loop with a capacitor, then you have an integrating amplifier. You know that the current is defined as the rate of movement of charge, Q, and for the capacitor the charge is Q is equal to C times V, where V is the voltage across the capacitor and C is the capacitance of the capacitor. So the current through the capacitor is equal to the change in charge divided by the change in time, which is equal to the capacitance times the change in voltage divided by the change in time. The potential difference across the capacitor is the potential voltage at the node X minus the output potential voltage. And for the ideal operational amplifier, we say that the voltage at node X is equal to 0. Just think of virtual Earth. And then the potential difference across the capacitor C is equal to the negative output voltage, because you have an inverting amplifier. So now we can say that the current through the capacitor is equal to the minus times the capacitance times the change in voltage output divided by change in time, or the derivative of time, should we say. We can also say, based on that we have an ideal operational amplifier, then we can say that the same current flows through the resistor as through the capacitor, because there is no current through the between the inputs. Then we can say the current through the resistor is equal to the current through the capacitor, with this equation here, where you have the input voltage divided by the resistance is equal to the minus times the capacitance times the derivative of the output voltage divided by the derivative of the time. So with this you have the definition for the current both in the resistor and the capacitor. And in this equation you also have the output voltage, and then we can find it by rearranging the equation so that it ends up looking like this, where we have the derivative of the output voltage is equal to the minus the parentheses of the ratio of 1 over R times C times the input voltage and the derivative of time. Now, if we integrate this equation, then we can see that the output voltage is equal to the output voltage at time 2 minus the output voltage at time 1 is equal to the minus the ratio of 1 over RC times the integral of where you have the boundaries of T2 and T1 times the input voltage times the derivative of time. And note that the T2 is the output at time T2 and V out T1 is the output at time T1. And you can say that the output is proportional to the integral of the input voltage. That is the area under a graph of input voltage with time. Would be right like this, where you have the input voltage on the y-axis and the time on the x-axis.